That's 6, 10, 16.
Guilty on all counts.
What?
Guilty on all counts.
For all counts, as in like murder?
Well, it's not first degree murder, second and third, and the third one has to do with creating.
Thank God.
In many ways, yeah.
I'm sorry?
In many ways. What about those cushions over there?
Oh, they're not. Oh, It has this nice empty
How
spot.
about a nice hard chair to sit in?
I'm fine. Hey, Victoria. Hey, Victoria.
Hi, Professor.
Did you kind of screw up the last lab?
Yeah, probably. I felt like I was going in a circle doing that lab.
Okay. You had your when you did the calculations using the mole thing, did the
Mhm.
calculations of the volume you should get?
Yeah.
You got like 185? That seem reasonable to you?
Yeah, it was around like 185, 184.
Yeah. Those are way
Yeah.
off. You should have gotten in the 500s. Okay.
Did I have to take like the square or the cubed of,
I got to look at it. I
Because-
got to see which way you guys were supposed to do that. Was this the one where you were trying to use the diameter to determine?
yeah. So it was, I looked at the example that, or it was in the lab, it had a picture of the flask with the balloon and they said use this
You
formula.
trust that more than you trust my PowerPoints?
I mean, it was in the lab. I don't.
You trust that more than you do my power. All right, I know where your loyalties lie now. Okay, let me.
I
gotta
mean,
get in.
I'll take the grade for what it is, but I think I'm having a case of it is what it is. If I mess up, I mess up.
I'll give you a chance to do it over again,
Okay. I will probably. I should
but
probably write this down.
it's not going to be a super thing. It's going to be for half the points. If you want to get in there and
Oh.
do it right now, I think you have a 75%, Victoria.
Yeah.
And literally speaking, we have one more lab, this one, and it
The-
should be fairly easy.
Yeah, titration I understand. I think limiting reagents for whatever reason, or
Well,
that lab.
that particular thing you were trying to make the calculation based upon the diameter of the balloon, I believe. Isn't that the one you were doing?
Yeah.
Okay. Student results. Okay. And you were supposed to go down here to the,
Mm-hmm.
I'm going to go 9. I'm going to use 9 because it's a nice even number. Okay.
Okay.
Now, there are 2 ways you can do this. I like, so pi r squared over pi r cubed, 4/3 pi r cubed.
Yeah, I did pi times
Pi
whatever
pi d cubed divided by 6.
Yeah, so I did pi times whatever we were given. So let's say 9 divided by 6, and then I would add the 1.
You have to do 9 times 9 times 9. That's diameter cubed.
I I thought, oh my God, I thought they were like giving, okay, because I
No.
was doing this lab also with a classmate. So she got it wrong as well because we were trying to figure it out.
Give me a call. Dear God. If you're trying to figure something out, I mean, go to the
Okay.
sources you have, then give me, I'll be honest with you. I was on the phone with Michael at 11 o'clock last night.
Yeah, I did it with Aaron Lewis last or yesterday, and we were just
1
like,
second. I want to see something.
okay,
I just want to see if Erin's in here, okay?
she's in the Thursday lab, so
She's in the Thursday lab.
yeah,
Well,
and
she's in the
I'm
Thursday lab. Try and let's see. Why can't I? Oh, there it is. Dear God, stop share. All right. Yeah, there's only you in here. Erin's not the world's best source to go with, Victoria.
I know. I'm trying
I'm-
to help her as best as I can,
Okay.
and it's more of like I don't give her the answers. I'm like,
Good for
okay,
you.
here's what you need to do because I don't believe in just giving someone the answer. I was never like that in high school or college. It's more of like I'm going to help you set up the problem and you tell me what you need to do next so that she can learn from it. And I was like, you're smart. I know you are. You have to get a C in this class. If you do well on the next exam in the final, I think you'll be okay. I don't want to completely give up on her.
Well,
Or
just keep on giving her encouragement because
yeah,
I really believe the next test definitely is not nearly as hard as the last one. The
okay.
third test is the ball breaker.
That was a bitch of an exam. Sorry.
I'm sorry. I make no
I
bones about it.
I was happy. I was surprised with my results. I was actually up at like at 3 a.m. when you finally released the final results of it. And I was talking with my boyfriend because I was like, oh, I got an 85, well, whatever. Then I was like, maybe it updated again. So I went to go check and I saw that I got like a 93, 94 on it. And I like started screaming because I was like so excited.
Well, good.
Because
Good.
I was like, hey, I would have taken an 85, no problem. But I guess I surprised myself.
Was that out of points or was that out of percentage?
I think that was out of percentage. I got a 94 out of it, or
Check on that
94%.
because it might be out of points.
Okay. I mean, it said that I got a 94% on the exam.
Then never mind. Then that's
Yeah.
fine.
So I was excited.
Anything you have to ask me about other than that?
No,
If-
I mean, if I can go back and fix the,
It's up to you, honestly, Victoria. Let me, I'm going to go in and look at your
My grade.
grades.
It's like a B right now. That's why I'm kind of like,
That's
you
not
know,
what I want. Did I lose it? Yep, I lost it. Okay. I need to get it back. Okay. Sorry, I'll look in and see your grades. I don't foresee you really needing it.
yeah, that's kind of what I'm like, if I understand what I did wrong and I can always, remember it for the next time and not worry about it. I'm not too worried about the lab.
Anything else bothering you about Lewis dots or anything like that?
I'm still trying to get used to it a little bit. I think I get confused of when to carry over the last set of valence electrons because it's like I'll have add them all up, and then depending on the charge, I'll either add or subtract one, and then or is it add and subtract one, or is it add and subtract like depending on the charge? So if it's like a -2 charge, do you add two?
You add two.
Okay.
Because
So
you have to have two extra electrons to give you the minus two charge.
so is it each element from the compound has to have 8 total, right?
I'm sorry,
On what each element has to
Yes.
have like 8 total. So
Yes.
we have to make sure that every side has 8 total
Uh,
besides hydrogen.
Besides hydrogen, each one of the elements needs to have 8.
Okay, so when you have your leftover electrons, that's where I get confused because I'm like, where do you make the bonds? So do you take
Okay, let's do something. All right.
okay.
Which one of the 5 other than OCN do you want to do? I'll do OCN. What the hell?
Yeah.
All right. Faith, how you doing?
I'm good. How are you?
I'm doing fine. Just taking Victoria through a Lewis dot structure. Okay.
Sounds good.
Victoria, this is OCN minus. So how many electrons does oxygen have?
6.
Carbon,
4,
nitrogen,
5.
and the electron, the minus charge, 1.
That's where.
It's a -1, so there's 1 extra electron there.
So how can you tell with covalent bonds?
How can you
Because there's
tell?
like, so like I was looking at the extra homework and it was like PBr3, and I was like,
Okay,
they're both negative charges.
what? I'm sorry. Was it just PBr3?
Yeah.
No, you don't understand. Victoria, when this thing has a negative charge beside it, that means it's an ion. Like if
Okay.
I had something like SO4 2-,
So
that's
Okay.
that's an ion. That minus designates that that particular species has 1 extra electron, so it's got a negative charge. It's got
So
1 more electron than it does protons.
So if it doesn't give us a charge, let's say, so like PBr3 didn't have a charge,
this
we
is
don't
the-
have to worry.
I'll show you one right now.
Okay.
Okay,
I'm
you
not
have
seeing your screen, by the way.
Oh, you're not? Sorry.
Yeah.
That would help. Okay, now are you seeing it?
Yes.
Now are you seeing it? Okay.
Yes.
You have SO3 and you have SO3 2-.
Mhm.
This thing, the SO3, just means you have a sulfur and 3 oxygens around it.
Okay.
The SO3 2- means you have a sulfur with 3 oxygens around it, but there's an extra 2 electrons in there.
Okay. So if
So
if there's no like designated charge next to it, so if I don't see like a +1, -1, then you
Right.
don't have to worry. Okay.
Okay,
Cool.
say we have sulfur has 6 electrons and the
Mhm.
oxygen has 18.
Okay.
You got that?
Yes.
So if I got a total of 24. Okay,
Okay.
so I'm going to put the sulfur in the center. I'm going to stick. By the way, this is the best I can do for this.
I got you.
All right, I got
Okay.
1 O there, 1 O there, and I got 1 O there. I'm going to do this. Okay,
Okay.
so I've just used up
6.
6.
Mhm.
So I have 18 left over, right?
Okay.
And
I can envision the numbers.
okay. Okay, now I've got 18 left over, right?
hmm
I'm going to put 1, 2, 3 around that oxygen. 1, 2, 3 around this oxygen. 1, 2, 3 around this oxygen. Okay, that's what I have to do.
Now,
Right?
is it just 3 total, or is
No,
it like
it's
3 pairs?
3 pairs.
Okay,
I'm literally going to put that there,
okay.
that there, that there. But it's a pain in the butt. That there, that there, this one. No, you don't want to be a big L. You want to be a little L. Okay, so I've got okay, I gotta pull these people in. Okay. All right.
So it seems like you just keep going around until they're all filled up with 8, and then with whatever is left over, you give it to S, or you give it to whatever's in the
Exactly.
center?
Exactly. What the rules tell you to do, fill your bond, get your bonds done first. I did that
Yeah.
by this one, and this one. That took 6 away. That left 18 electrons. The next rule says I put them around all the terminal atoms. 2, 4, 6, 8, 10, 12, 14, 16, 18. I've used up all my electrons.
Yeah.
The trouble is one of my sulfur only has 2, 4, 6 electrons around it. So I have to take one of these guys away and I have to make a double bond.
Oh, okay.
Okay.
I'm sitting there going like, do I put like the dots on the top, the bottom? When do you make it a double bond? When don't you make it a bond?
Okay. Now, if I'm dealing with this guy, instead of having 24, I have 2 extra electrons. So I have 26 valence electrons.
Mm-hmm.
Okay, so I've knocked 26. I just used up 2, 4, 6. That gives me 20. I put my, no, not a semicolon. Thank you. Put my electrons around my terminals.
Okay.
Stop that. The difference here, all right, okay. The difference here is that all right, now when I'm dealing with SO3 2-, I got 26 valence electrons, 2, 4, 6, that leaves me with 20. I just used up 2, 4, 6, 8, 10, 12, 14, 16, 18. I have 2 left over. So the difference between the two is that this has a lone pair around the sulfur.
Okay.
And then what I would do is I would take brackets and put 2- there.
So if the center cannot be fulfilled with a total of 8, that's when you can make a bond, like a double bond, correct?
Correct.
And then, but if it has enough, like if it has 26, you can put it on the bottom, let's say, to satisfy its need of 8 electrons. You don't have to do like a double bond or anything like that.
Exactly.
Okay,
Exactly.
I understand now.
If you count,
I think I was so out of it last week. I'm sitting there going, yeah, okay, I get
No,
it.
no, I understand it. Believe me, this stuff is kind of fairly new. So I understand it completely. Anybody else have any questions, guys? Lewis, thoughts?
Thank you, Professor.
No, hey, that's what I'm here for. I'm here to make sure you guys understand this stuff. Any other questions? Oh, I'm in a different environment today. Can't you see it's real bright here now? I'm not in my bedroom. My wife let me out. Hooey.
Yay.
Okay, guys, we're going to continue. I'm going to continue on with another question. This is somebody was groveling at me there. We're going to do OCN. All right, and by we, I mean emphasis on the U. Boom, come on, new slide. Yes, thank you. We're going to do OCN minus, okay? Mila, how many valence electrons does oxygen have?
Honestly, I'm not sure right now.
Okay, fair enough. Okay, so how many valence electrons? Guys, you should be having your periodic tables out.
Are there 6?
6. Okay, how about carbon? Somebody asked me, tell me how many carbon has.
4?
4. And nitrogen.
5.
All right, now I have this little thing out here, this little negative sign. So I have an extra electron. I got to add that too. So I got valence electrons. I have 6 plus 4, 10 plus 5 plus 1. I have a total of 16. Which one of the elements is going to go in the center?
Carbon.
Okay. Now, I've used up how many bonds now? I've used up how many electrons?
4.
I have 12 left. Where do I put those 12 now?
Around oxygen and nitrogen.
Okay, somebody other than Victoria.
Look at you.
Okay, I'm going to put my little dots around. Put them around the terminal. I've just used up 2, 4, 6, 8, 10, 12. I don't have any left, guys. Is this a good structure? Somebody other than Victoria.
No,
Why not, Jennifer?
because there has to be 8 around the middle element.
How am I going to fix it, Jennifer?
You can you can bring 2 electrons from each, or like 2 from the oxygen and 2 from the nitrogen, and make double bonds in between instead of single bonds there.
So what you're saying is I could do this. And that. Does this work? Guys, does this work?
Yes.
Remember, guys, I can't really I can't really illustrate it because I don't have the capabilities. But if you were drawing this, you would put a bracket around this entire molecule with a negative sign out there. Now, I wasn't going to teach you something, but I'm going to teach it to you anyway. I'm going to teach you something called formal charge. Okay? We're going to learn about formal charge. By the way, can I make this? How do I do that?
Are you trying to do a triple bond?
Yeah, I'm trying to do a triple bond.
What if you underline the equal sign? Like highlight the equals? and then
Very
the
good.
question line?
Very good. There we go. And there's only one slight problem with that. Okay. Is there another way I can draw this molecule? Is there another way I could draw this?
You can do a triple bond then on nitrogen side instead of oxygen.
Does everybody see that?
Aren't you also missing, I think, 2 electrons above the O, the oxygen?
No. I'll explain that in a second, okay?
Okay.
But the nitrogen in the middle is not balanced.
Well, one second. Okay. Yeah, you're right. The nitrogen is not balanced. You are correct on that. Okay, now they're balanced. And I have 16, 2, 4, 6, 8, 10, 12, 14, 16. 2, 4, 6, 8, 10, 12, 14, 16. Both of these have 16 electrons around them, and each one of the elements has 8 electrons around it. Okay?
So could we have it either way?
That's what formal charge is going to tell us. Okay? Formal charge is the charge on the atom as it exists in the molecule. Okay? That's all formal charge is. It's a way of calculating the charge on the atom as it exists in the molecule. Okay? And the way we do this, formal charge is equal to the normal valence electrons minus the lone pair electrons plus the bonding electrons divided by 2. Okay? Normal valence electrons. Now, when we're talking formal charge, we're talking about the element that is the one of the atoms that we're talking about. Okay? That is what we are dealing with. So let's just consider this oxygen. Formal charge on that oxygen. How many electrons does oxygen normally have around it?
6.
6. So I go 6 minus. How many lone pair electrons are around that oxygen?
8.
No, lone pairs. How many electrons are specifically on oxygen and not shared?
4.
4. Just this pair and this pair. Okay. Now, how many bonding electrons are between the oxygen and the carbon?
4.
4. So 6 minus 4, I'm sorry, excuse me. Sorry, this is a bad. Stop that. There we go. So my formal charge is going to be 6 minus 4 plus 4 over 2, or 6 minus 6. My charge on this oxygen is going to be 0. Now let's deal with the carbon. Okay. Carbon's formal charge is going to be, how many normal valence electrons around carbon?
0.
No.
Oh, wait.
4.
There's
Normally-
4. Sorry, 4.
So it's going to be 4 minus, how many lone pairs does this carbon have?
0.
How many bonding electrons does it have?
4. 8.
So how much charge is on that carbon?
0.
All right, now let's figure out the nitrogen. How many valence electrons are around nitrogen normally?
5.
Somebody other than Victoria. How many lone pairs does that nitrogen have? Electrons that are exclusively to it that it's not sharing.
4.
4. How many bonding electrons does that nitrogen have?
4.
So five minus 4 plus 2 divided by 3. I've got a -1 formal charge on that. Do you see how the formal charges work? All right. Now, we're going to do the next compound. How many valence electrons does oxygen have? Guys, I shouldn't have to wait for this.
6.
Thank you. How many lone pairs does this oxygen have?
2.
How many bonding electrons does it have?
6.
So this is going to be 6 minus 2 plus 3. I have a +1. That's an excited one. Okay. Now let's look at the carbon. How many valence charges on carbon? Valence electrons.
4.
4.
How many lone pairs? Lone pair electrons. How many electrons does carbon have around it that are not involved in bonding?
0. 0.
How many bonding electrons does it have?
8.
So I get 4 minus 0 plus 8 over 2. The formal charge on carbon is 0. Let's look at the nitrogen now. By the way, this should have a lone pair under here. This lone pair is there. So how many valence electrons does nitrogen have?
5.
How many lone pairs does that nitrogen have?
6.
Thank you. How many bonding electrons does that nitrogen have?
2.
So the formal charge on this nitrogen is going to be a 2 minus. By the way, if you notice something, when we figure out the formal charges, add up all the formal charges, they're going to be equal to the charge on the substance we're dealing with. All right. How about this oxygen over here? How many valence?
6.
6.
Lone pairs?
6.
Bonding electrons?
2.
2.
So the charge on this oxygen is going to be a 1 minus. All right, let's carbon. Valence electrons.
4.
How many lone pair electrons?
0.
2.
Bonding electrons.
2.
Bonding
Or wait, sorry.
electrons.
I was
How
looking
many-
at the wrong thing.
8.
How
8.
many bonds does it have? How many bonds does that carbon have?
It's got 4 bonds, so it should be 8
8.
electrons.
8 divided by 2. So I got 4 minus, basically 4 minus 4. That charge is 0. Let's look at the last one. How many valence electrons?
5.
Guys, you should be answering this with me. On this nitrogen, how many lone pair electrons?
2.
And how many bonding electrons?
6.
Okay, Rosina, you asked the question, how do we know which spectrums, which one's the best?
Yeah.
This is the way we do it. By the way, this gives us 0 charge on the nitrogen. All right, now there are 2 rules when we're dealing with formal charge. When we are considering what the best structure is. A Lewis structure in which all formal charges are 0 is the best one. Small formal charges as opposed to large ones are better. Formal charges should be consistent with electronegativities. So write these 2 down. Small formal charges are preferred to large ones. Formal charges should be consistent with electronegativities. So if we're going down to our compound, this one, that's fairly good. I got a 0, 0, and a -1. I can't get any better than that. This one, I got 1 plus 0 and 2 minus. Now, when I say small formal charges, I'm not saying what the overall, when you add all these formal charges up is. I'm saying that the amount of formal charges and the number of atoms that have formal charges. Do you see that this one with a 1 plus, a 0, and a 2 minus has a lot of things that has lots of formal charges on it? So that means it's less stable. Now I look over at this one. And this one, I've got a -1, a 0, and a 0. Same thing as this one. One major difference. What has more electronegativity, oxygen or nitrogen?
Oxygen?
Oxygen.
Oxygen does. So therefore, if something's going to have a negative charge, is it going to be the oxygen or the nitrogen?
Oxygen.
So which of these structures is the preferred structure?
The last one.
The one that's on the right.
Yeah.
Okay, do we have a good concept of this, or do you want me to go to another example?
Professor, there was a problem in the extra homework assignment, BSF, and
I'm
although
sorry,
I haven't
what
gone
is it?
through BSF, boron, sulfur, fluorine.
Okay. Oh dear God. You mean I have to figure that out? Okay, we'll go for it. BSF. Okay, which one is the least electronegative? Is there any charge on that, Rosina?
Sorry,
charge
there
on
wasn't
it?
a charge. No
All
charge.
right. So which one do you think has the least electronegativity?
Boron.
Boron.
Okay, good choice. I'll go with that. Put that one in the center, okay? Now, boron has how many? You're gonna have to answer this because
Three.
three?
Yeah.
Right. So we have 3 plus how many sulfur have?
6,
Plus how many fluorine have?
7,
So we have a total of
16.
16. Okay. All right. I just used up 4 of them, so I have 12 left.
Right.
Okay. I'm going to put them around the terminal atoms. Okay, I put 2, 4, 6 around fluorine, 2, 4, 6 around sulfur. I don't have any more left, right?
Right.
So I am going to have to make double and triple bonds out of this, correct?
That's right.
All right. Now I know for a fact that I'm going to end up doing this.
That was my question. How do you know for a fact that you can have double or triple bonds between boron and sulfur, and why not between fluorine and boron?
No, why not between what and what?
Fluorine and boron.
Because I know that formal charge wise, if I put a double or triple bond here, that is pulling formal charge away from fluorine. That's going to make fluorine that much more positive.
But we would actually have to calculate the formal
would have to
charge to figure
calculate
that
it.
out, right? Okay, got
Yes.
it. Thank you.
Yes, you would have to calculate. Yes. Could you have this? Or could you have this?
Yeah, mine looked where
either
there were triple bonds between boron and fluorine, and a single bond between sulfur and boron.
If I do that though, Rosina, if I do that, and I try and calculate the formal charges around there, it's going to be horrendously bad for fluorine and sulfur.
Got it.
All
Got
right.
it.
So if I'm going to do this, I'm going to calculate fluorine. Fluorine has normally how many valence electrons, Rosina?
7.
Okay. How many lone pair electrons does it have?
2.
How many bonding electrons does it have?
6.
So fluorine is going to have a 2+ charge.
Right.
Let's figure out the boron.
Boron is going to be 3 minus lone pairs are none, 0, plus 6
Nope.
divided by 2.
Nope.
Oh, sorry, 8
6.
divided by 2.
So I've got 4 minus 3. This is a 1 minus. Okay. And I
Yeah.
do this. The last one, the sulfur, that's going to be equal to, go ahead. How many lone pairs? Or how
That's
many?
going to be 6 minus 6 plus 2 divided by 2.
And that makes a 1 minus for that. So basically, what you're telling me is the most electronegative atom in creation is going to have a +2 charge, while boron, which is almost a metal, has a 1 minus, and sulfur, when it's in the same molecule as fluorine, has a 1 minus. It's not going to happen.
Right, doesn't make sense.
If we do this one, okay, and I change some numbers around here. Wait a second, that's 6. Yeah, that's right. So that is still going to be 1 minus, and this is going to be okay.
Yeah,
All right.
this definitely looks better than the other one.
All right. So we're going to do the last one, which has this. Okay. My fluorine in this one. Remember, this was 0. This one was 2 plus, 1 minus, 1 minus. Okay. So if I'm dealing with this one now, that's going to be one plus, boron's going to be still 1 minus, and the sulfur is going to be, nope. So this one, the bottom one is going to be okay. Bad
Yeah.
situation, Rosina. Best option is this one. Okay. That is going to be your best option. And more than likely, I think something funky happens. And I think what happens is we disobey this is going to be one of those that disobeys the octet rule, and it's not going to be one you need to worry about. But I think what really happens here is this. Yes, I know boron doesn't have, I know boron does not have man. I know that boron does not have 8 electrons around it. But literally speaking, if you do this in this fashion, it works out better. Trust me.
Got it.
But that's
Thank you so
something
much, Professor.
you would not know that. You would answer the question the way I answered it originally, okay, Rosina?
Got it.
Anybody have any problems with formal charge? Does it seem that difficult a concept? Formal charge?
Is it quantum
ahead.
mechanics though?
Hunter,
I'm sorry. I know I was a little bit late.
I want you to look at the video, okay, Hunter? Because I
Okay,
have to get on with
Yeah, no
Vesper.
problem. I'll look at it after class.
Or stay after a second or two, okay, Hunter?
Okay, sounds good.
Okay. Are we good with this now? Any more questions about Lewis dot structures?
Professor, there was one more question in the extra homework problem.
Okay.
Are we going to be doing that today? It was SF6, and
No.
it did not seem to
No,
follow
I
the
told you,
optics rules.
there were 3, there were definitely 2 that you didn't have to do.
Okay, good.
One was SF6 because what happens is that violates the octet rule. That's something that you are going to learn next semester.
Okay, great. Thank you.
You can violate the octet rule, but you're not going to do that. Any
All
other
right,
questions,
we'll stay
guys?
clear.
What?
We'll stay clear.
I'm still didn't hear you.
We'll stay clear of violating the rule.
Yes. Anything else with Lewis dots? All right, you need Lewis dots to do the next thing we're doing. We're going to be getting into valence shell electron pair repulsion. All right. Victoria, why are you
Antagonizing
frowning?
my dog. Oh, I'm frowning because in chat.
Yeah.
He told me I wasn't allowed to answer anymore, so I
Ah.
frowned.
All right, guys. First of all, everybody, pictures. I want to see video. I want to see video, ladies and gentlemen. Alec, Rosina, Marie. Jennifer, thank you. Neela, thank you so much. Now, right now, I want you to hit on the bottom panel. You should have a button that says reactions. Right now, I want you all to clap your hands. Thank you. This is going to do something for me for next semester. And that is, I'm tired of you guys logging in and then going away. So I get to say, clap your hands every now and again. Sorry, that's just a little smugness coming from me. I gotcha.
Can we get a visual? Can we get a visual?
Yeah, it's just hit the clap your hands emoji. That's a visual. Andrew, Hunter, do you have a question?
No, I was just checking out the little emojis. I noticed if you raise your hand, it puts your camera on view.
There we go. So honestly, guys, that works. You have a question, hit the raise your hand thing. I gotta go then find you and then I'll call you up. So that's a good thing. All right, so Kaylin, do you have a little brother or sister? You have a brother or sister, Kaylin?
Yes.
All right, if you're in the car, are you snuggled up against each other?
No.
Where are you at? You're at one window and he's at the other, right?
Yeah.
Is it he or she?
She.
So in the car, you're as far away from
yeah.
one another as. Do you think atoms are any different? Do you think atoms like each other?
No.
They want to get as far away from one another as possible. Does that make sense?
Yes.
Absolutely. So we're going to show a theory that is called valence shell electron pair repulsion theory. And in order to do this, we got to define some terms. A domain or an electron cloud. I don't like domain. I'm going to call it electron cloud. I'm in the clouds. Okay. So an electron cloud is every lone pair counts as one electron cloud. A single, double, or triple bond is considered one electron cloud. So if I am looking, I'm going to stop share for here for a second. If I am looking, oh, I got rid of it. Why did I do that? Oh, I was right there. Okay, Lewis. No, that's not what I want. That's what I want. All right. So, guys, if I am asking you, don't look so bored, Kaylin. I just gave you attention a second ago. Now, what you have to do is you have to draw the Lewis dot structures to do any of this any good. All right. Let's look at the center atom here because we're going to be looking at center atoms. Remember what I defined an electron cloud as: a lone pair or a double, triple, or single bond. That's silicon, or that's selenium. Katie, how many single bonds does the selenium have around it?
2.
No, this is a double bond. That's a single bond.
4.
And now, how many bonds? How many single bonds does it have?
1.
It has one single bond. That single bond counts as one electron cloud. All right, Mila, how many double bonds does that selenium have? Yes, I saw it. I saw your answer. She said 1. There is one double bond. It also counts one electron cloud. How many lone pairs does that have around it? Cash? How many lone pair electrons does the selenium have around it?
2.
Lone pairs, not lone pair electrons, lone pairs.
1.
1. It also counts 1. So there are literally 1 from the double bond, 1 from the single bond, 1 from the lone pair. If I was going to draw something like water, which is H2O, In order for me to draw H2O, if anybody wants to buy me a molecular making kit for Christmas, I would accept it. Okay, Marie, let's look at oxygen. That's the center atom. How many electron clouds does it have around it? How many single bonds?
Let's say 1 electron cloud,
Now, how many single bonds?
2,
Two. Two separate single bonds, 2 electron clouds. Now, Marie, how many lone pairs does it have?
2,
It has 1 lone pair, 2 lone pairs. So it has 2 electron clouds from each of the single bonds. It also has 2 from each of the lone pairs. So water has 4 electron clouds around it. All right, some other things that we need to get down. A lone pair is a non-bonding pair. It's an unshared pair. In other words, it's the electron pair that is not between atoms. It's located entirely on one of the atoms. Bonding pair is just an electron pair that is involved in bonding. So if I have 2 things, Faith, I have 2 things around a center atom. How do they get as far apart from one another as possible?
I'm sorry, I'm a little confused. What did you say?
If I have, why is this not stopping?
I have a. I think I could maybe answer it.
1 second.
I just didn't figure out what he said.
There we go. Yeah, that's what I want. Okay. I have 2 things around a center atom. How do I physically get them as far away from one another as possible?
When you say things, are you talking about what's connected to the atom?
Yes.
The movement of them. I mean, the
No, how
electric
do I get them far apart?
energy. You have to introduce
No.
Magnets?
What shape do they have if they are as far apart from one another as possible?
A line. You pull them apart.
Like a
If they
parabolic
look at
shape.
this, guys, if I have one in the center and I have them opposite one another, isn't that as far away from one another as they can get?
Yes.
So if I have 2 electron clouds, because the atoms want to get as far away from one another as possible, they're going to exist in a straight line, or the shape is going to be linear. If this one tries to move up here, this one's going to move away from it to stay in the linear shape. The bond angle between from one of the atoms to the other is going to be 180 degrees. Does this make sense to you all? If I have 3 things, if I put another atom in there, again, we're thinking about the car analogy. If you have 3 kids in a car, one poor schmuck sitting on the hard seat in the center, and the other 2 as far on the windows as the other, right? I put another atom in here. What does that do to these 2 atoms? They want to get away. How do they get away, Kaylin? I'm attacking this center molecule with another atom. Where does that make these two go?
Diagonal away from each other.
They're good.
Triangle.
They're gonna find a balance. Like they're gonna equal out so that it's not
So
far.
they're all three, right,
Yeah.
Hunter? You're absolutely right. They are going to be as far apart from one another as possible. The way that you have that is you have them in like points on a triangle. Does that make sense to you all?
Yeah, but I
Can
have a
you get
question.
them further apart? They want to get as far apart from one another as possible, so they go to the points of a triangle.
I have
And
a
this
question.
shape is called trigonal planar.
Hey,
Bond angles. I have 3 bonds, and this whole thing is a circle. So each individual bond angle is 360 divided by 3, or 120. Hunter, you had a question.
yeah. So I mean, theoretically, should there be like a limit on that? Because if you cram too many in, they're not gonna have like room to distribute like that space apart. So is there cases where there's too many
Okay.
of those atoms together?
Hunter, I put another one in here. What's the bond angle going to be? If I put a third one in and it made it 120, what's the fourth one going to do?
Make it 180?
No.
Or how many degrees does it oh, okay. So then it would be 240?
Hunter, I think you need to retake geometry.
Sorry. 360?
How do I get this? If I put a fourth one in here.
Or how many do they equal each?
Would it be
90.
90?
You said
So
90?
the number I was trying to come up with is 90.
Oh, sorry. I just didn't know if we were going up and down.
So if I put a fourth one in here, what is that going to look like?
Quadrant angle.
Remember, 3 points make a plane. If you get a fourth point, we can involve the third dimension. Up to this point, 3 points make a plane. We're all on one plane. I add a fourth thing in there, I can invoke the third dimension. So what happens is I get this normal, the normal thing, the normal planar one with the 3 in there. I have another atom come in here. It pushes the other 3 down, and it pushes them down at an equal rate, so that you get this kind of like pyramid that appears from these bottom 4, and you got this 1 up there. But if I flip this, and this are also a pyramid. This, and this are also a pyramid. You go in the back side, this one, and this one. You got 4 pyramids that are put one on top of the other. 4 domains makes tetrahedron. 4 electron clouds around the center atom makes it tetrahedron. So it's very, very simple. 2 things around the center atom. You have an electronic geometry of linear. They want to get as far away from each other as possible. 3 things around the center atom. You have trigonal planar. 4 electron clouds around the center atom. You have something that looks like a tetrahedron. Now, we have to realize what is happening. If one of these things that's attached to the center atom is a lone pair, I can't see it. So I also want to know what I'm seeing in terms of the atoms. So if I have three things around the center atom, all three are atoms, then obviously I can see all three of them. And the electronic shape is trigonal planar. The molecular shape is trigonal planar. But if I take one of these atoms away and replace it with a lone pair, I can't see the electrons. All I can see is the red ball going to the blue ball, going back to the red ball. And that has a bent shape. So if I have three electron clouds around my center atom, all three are atoms, I have this electronic shape, trigonal planar. I also, if all three things are atoms, the molecular shape is trigonal planar. If one of those three clouds is an electron pair or a lone pair, I can't see it. So all I can see is the red ball going to the blue ball, going to the red ball, a bent molecule. Now, if I have a tetrahedron, 4 electron clouds around the center atom, that means my electronic geometry is a tetrahedron. I take one of them away. If I take one of them away, I can't see it. All I am seeing are 3 points and 1 point at the top. I have a three-faced pyramid so that its molecular shape is trigonal pyramidal. Its electronic shape is still tetrahedron, but one of the sites is occupied by a lone pair, so its molecular shape is trigonal pyramid. If I take 2 of the sites away in a tetrahedron and I make them into lone pairs, I can't see them anymore. If I can't see the 2 extra lone pairs here, all I am seeing is the white ball I'm seeing the white ball going to the red ball, going to the white ball. It is bent. Now, couple other things about bond angles. If I have a tetrahedron, the angles are equal and they are 109.5. If I have a lone pair out here, it pushes down on those atoms greater than if that was a regular atom up there. Lone pairs have greater push effect than atoms do. So it pushes those down. It makes these bond angles a little closer. If I have a tetrahedron, I got 2 bond pairs out here. That pushes even further. That bond angle gets reduced even more. So I have two different types of bent molecules. One comes from a trigonal planar because I can't see one of the things out here. I can't see the one lone pair that's out here. The other kind comes from tetrahedron when I have two lone pairs that I can't see. This is the slide you need. Memorize it. What you are going to do strategy-wise for doing VSEPR, you're going to draw a Lewis dot structure. You are going to count the clouds around the center atom in the Lewis dot structure. You're going to first predict the electronic geometry because the number of clouds is the same as predicts what the electronic geometry has to be. The second thing you're going to do is you are going to mentally erase the lone pairs and realize that the shape will be different if you have lone pairs. Two electron clouds. The electron shape is going to be linear. It doesn't have lone pairs. Molecular shape is going to be linear. Three electron clouds. You have a electronic trigonal planar shape. If you don't have lone pairs, the molecular shape is trigonal planar. Notice, every time you don't have any lone pairs around the center atom, the molecular shape is the same as the electronic shape. Three electron clouds, electronic shape, trigonal planar. If one of those clouds is a lone pair, I get a bent molecule. Four clouds, that leads to a electronic shape of tetrahedron. No lone pairs, molecular shape tetrahedron. Four electron clouds, electron shape has to be tetrahedron. One lone pair, trigonal pyramid. Four electron clouds, electronic shape tetrahedron. If two of them are lone pairs, I have a bent molecule. Any questions on that? Questions on this? Does it seem okay, guys?
Professor, just curious to know what's the difference between, visually, what's the difference between trigonal planar and trigonal pyramid? They should look pretty much the same, right?
No. Trigonal pyramid is a three-dimensional shape. These three balls that you're seeing there, Rosina,
Yeah.
are below the plane of the molecule. When I have trigonal planar, they are all on the same plane.
Oh, got
All of those atoms are on the same plane.
it. Got it. Thank you.
Okay? Last concept we have for this block is polarity. And polarity is nothing more than the property of a covalent molecule which orients movement of the molecule in a magnetic field. In other words, you have a positive end of the molecule and a negative end of the molecule. So if you put it in a magnetic field, the molecule will rotate so that the positive end of the molecule is facing the negative end of the magnet. Got time. Stop share. I'm going to re-show you a video. Come on. My favorite video, so you get to see it twice.
Welcome to Dogs Teaching Chemistry. Our first lesson is chemical bonding. Chemical bonds are what holds atoms together. A chemical bond is an attraction between atoms that allows the formation of a chemical substance. The electrons that participate in a chemical bond are called valence electrons. These are electrons that are found in an atom's outermost shell. Let's take a look at the types of chemical bonds that can be formed between atoms. An ionic bond is formed when one of the atoms will lose its electron to the other atom. This results in a positively charged ion, called a cation, and a negatively charged ion, called an anion. Positive and negative attract, and the result is an ionic bond. Covalent chemical bonds involve the sharing of a pair of valence electrons by two atoms. There is also what is called polar covalent bonds. These are covalent bonds in which the sharing of the electron pair is unequal. The result is a bond where the electron pair is displaced toward the more electronegative atom. Thanks for watching, and we'll see you guys next time.
Okay, thank you for indulging me. So, what happens is molecules have electrons that are unequally distributed. When they are unequally distributed, like the one dog pulling the other one over towards it, that means that you have an unequal sharing of the electrons. You have unequal sharing of the electrons. That means you have that bond exhibiting a negative and a positive side. So when you have polarity, polarity is the main property that dictates solubility. It is that concept, like dissolves like, unlike dissolves not, it doesn't dissolve anything. So if I have a molecule that is polar, it has charges on it, it is going to more likely dissolve those things that are polar and those things that are ionic, because polar and ionic have charges. If my solute is nonpolar, it won't dissolve polar and polar and ionic. What it will dissolve is something that it is like, which is other non-polar compounds. So there's another concept we need to consider this. Okay? Say we have a bar. We have a bar here. Where am I at? Do you see my pen, guys? Can you see my pen? Now, if I have both ends equally negative, and I have a positive pole up here and a negative pole here, yeah, the negative end is going to want to drift to the positive end. But look, this end is also negative, and it's getting closer to the negative pole here. So am I going to get any movement here? You might like to think of it like if I had 250-pound men that were tugging on a rope. The center of the rope's not going to move because they're tugging equally and opposite. So in order for something to be polar, you need to have electronegativity differences. You need to have polar bonds, and we need to have asymmetry. So if I have a carbon dioxide molecule, Yeah, the oxygen on either side is more electronegative, so it pulls equally, but it pulls equally and in opposite directions. I don't get any movement. Carbon dioxide has polar bonds. It's symmetrical. If a molecule is symmetrical, it can't be polar. For polarity, you have to have asymmetry and you have to have polar bonds. Now, guys, if you're going on to organic chemistry, and this is the only reason I would ever suggest that you do it. In organic chemistry, there are some funky things that you're going to have to learn to be able to think spatially by. So they make things called molecular models. And you can spend upwards of $350 to $500 for these molecular model kits. Do not do it. Buy yourself a bag of pretzel sticks and marshmallows and stick it in that way. It will help you. And besides, when you're done at the end of the evening, you can eat the profits. That's pretty much all I have to talk to you about with VSEPR and Polarity. Why don't we end early tonight, guys? Unless you have questions. Are you vaping? This is a no vaping zone. What can I say, Katie? Seriously, does anybody have any questions about VSEPR? About being able to predict molecular geometries? Guys, please pay attention to this slide. Copy it. Do something with it. This is going to tell you all the information you need. All you have to do is be able to draw the Lewis dot structures and have this slide, and you'll have all the information you need. Guys, that's it. How's it going, Neela?
Oh, it's great. I got like toddler fight club on the couch right now.
I was
Sick.
actually adjusting.
I said it too.
I was actually adjusting Neela, but I was watching the wrestling tournament.
Yeah, but
I'm doing pretty good.
You're doing pretty good, Neela?
Pretty good.
Good. Who's the better wrestler?
honestly, my younger one's a lot tougher.
Are you going to stand for that?
They're crazy.
Go kick mommy in the hips.
They're wild.
Of course they are. Guys, I've got nothing else for you. So if you want to get out of here, that's fine.
Bye.
See you in lab.
Bye.
All right, I'll see you in the lab.
See you in the lab, guys. Bye.
2 shares.
Sure. Good night.
Good night, Mila. Shamira, Omar, Gaith, are you still here? Gaith. I think you need a visual, Gaith. I think you need to get back on Zoom to get your visual. Bye.